Okay, let's talk a little bit about disinfection. This would be Chapter 10 in the OTCO Basic Wastewater course. The OTCO material primarily focuses on chlorination with a little bit about ozone and ultraviolet radiation. I'm going to talk mostly about chlorination and ultraviolet radiation because those are the two forms of disinfection that we've used here at the Perrysburg plant. And I think those are probably the two most widely used forms of disinfection around Ohio. So let's go ahead and get started. So why do we need to disinfect wastewater? Well, of course, primarily to remove pathogens from our discharge, which of course pathogens are defined as any type of organism that causes disease. Um, Diseases that can be caused by pathogens in wastewater include dysentery, hepatitis, typhoid fever, gastroenteritis. All of those can be caused by pathogens that would occur in wastewater. So we want to remove those pathogens to make our discharge safe for water contact. Of course, uh, if you're working somewhere that has an NPDES permit, you're likely discharging to some sort of receiving water. Uh, Here at our plant, it would be the Maumee River, but smaller plants maybe discharging to directly to Lake Erie or even ditches or small streams. So disinfection, trying to eliminate those pathogens and make our discharge safe, primarily for human contact with water recreation. I guess also the possibility that you want to remove pathogens before, say, your discharge could be taken up in a water treatment, like a drinking water treatment intake. So secondary treatment actually would remove, in a lot of cases, the majority of pathogenic material, but we're still going to have some leftover that we need to remove. So that's why disinfection. Um, Actually, here at our plant, and probably most plants around Ohio, we are not required to disinfect for a couple months of the year in the middle of the winter. Chlorine uh, is less effective in cold weather. Also, in the months of December and January, water contact recreation is pretty unlikely. Here in Perrysburg, we use that time to maintain our system. Uh, Now that we switched from chlorine to UV disinfection, I wouldn't be surprised at some point to have to disinfect 12 months out of the year. But currently, 10 months, beginning at the end of February. Actually, March 1st is when we have to start, and we are done November 30th. As far as disease-causing bacteria in wastewater, I guess Zachary Taylor, President of the United States back in the 1800s, actually died. They think from gastroenteritis or maybe dysentery. And the theory is that with open sewers in Washington, D.C. at the time, or I had read that the water intake uh, that they used to provide drinking water for the White House was actually just downstream from where the sewers discharge in the Potomac River. So that's one relatively famous case of somebody becoming ill by coming into contact with some of this pathogenic material. So the two technologies that we've used here at our plant since I've worked here would be chlorination and UV disinfection. There are positives and negatives to both, which I've outlined here on this slide. Of course, the main positive for chlorine is that it's relatively cheap and also very effective. Um, Negatives are that it's toxic, not just to aquatic life, but to human life as well. So it's very dangerous from a safety standpoint for operators that have to work with chlorine. Uh, if you store enough chlorine on site, you actually need to develop an emergency response plan uh, that details how you would respond to any leaks in the system. Requires a relatively high level of training for the plant operators and a lot of specialized PPE to be able to change uh, 1-ton cylinders or to switch from empty cylinders or larger plants like City of Toledo. I know get chlorine deliveries in rail cars. So definitely dangerous, but as I said, the main benefit is that it's relatively cheap. Also, because it is toxic to aquatic life, most plants that have chlorine disinfection are required to uh, basically remove any chlorine residual before discharge. So uh, you inject chlorine into the flow to disinfect it, and then we have to remove it before we discharge it into the river. Uh, at least we did when we had chlorine here, just to protect aquatic life uh, by the wastewater plant outfall. UV disinfection positives are that it's much safer than chlorine. There is no associated toxicity for aquatic organisms. Uh, Negatives are that it's fairly expensive. After your initial capital cost to install it, their replacement cost for the bulbs. I know in our case we probably spend $20,000 every couple of years just replacing bulbs. They have a useful life of anywhere from 10 to 12,000 hours, and once they reach that end of their useful life, they have to be replaced. Also, of course, requires a fair amount of electricity to power them, and they need to be on around the clock during disinfection season. Uh, we do a fair bit of maintenance on the system, cleaning bulbs, removing algae from the channel, stuff like that. So definitely more expensive than when we used chlorine, but the trade-off as far as safety was something that the city was willing to pay for. Uh, so we'll go into a little bit more depth about chlorine. If you've done the math homework already, you've heard me say in doing the math problems, this equation, the dosage equals demand plus residual. Uh, Let me expand on that just a little bit. I don't think you're going to need to get into too much detail about the chemical reactions that occur with chlorine on a class 1 exam. But basically, chlorine is very reactive and it'll react with a lot of different constituents in the wastewater stream. Ammonia, uh, ferrous ions, if you use ferric or ferrous chloride for phosphorus removal, nitrites and nitrates, if you have those in your flow after nitrification to remove ammonia. So chlorine is very reactive, and all of those different reactions create what we call chlorine demand. So satisfying that demand, uh, what you're left over with, if you've satisfied demand and you still have leftover chlorine, is called the residual. So the operating principle uh, in using chlorine is to feed enough chlorine that after the contact time, and chlorine does take a fair amount of mixing and contact time to be effective, At the end of that contact time, you want to have some residual left over. And if you have residual chlorine left, then that generally tells you that you've fed enough to get adequate disinfection. Now, every plant is a little bit different, so I imagine your plant or a plant that you would work at would have a target residual. Uh, I believe I recall back when we had chlorine here, we looked for a target chlorine residual of around 2 to 3 milligrams per liter exiting the chlorine contact tank, and that told us that we had enough chlorine being fed to get good disinfection. But basically, it's a process of trial and error, measuring that chlorine residual, uh, and then testing alongside the testing that you have to do to prove that your disinfection system is working. And like with most other things here at the plant, the EPA gives you a limit. So we test for E. coli. Uh, so these are indicator organisms, E. coli or fecal coliform, that are easier to test for than the actual pathogens in the wastewater. And by doing that test, if we meet our limit, we know if we're eliminating those indicator organisms, we're also eliminating the pathogens that are in the wastewater alongside those indicator organisms. So, as I said, it's kind of a process of trial and error, feeding chlorine, uh, seeing how much of a residual you have left over after the contact time, and then testing for those indicator organisms alongside that, and trying to find what type of residual you need to have to meet your limit as far as the indicator organisms go. So after you've injected chlorine and had it go through the contact process, and most of the time there's going to be a chlorine contact tank with baffles to redirect the flow and get good mixing and adequate treatment time. You can see here on the slide that we're looking for contact time between 30 and 60 minutes at design flow, and at least 15 minutes during peak flows. Uh, After you've gone through all of that treatment process, most plants have to remove the residual chlorine before they can discharge. We had a chlorine residual limit here. I believe it was around 0.1 milligrams per liter. I don't really remember exclusively, but a lot of times you're going to have to add sodium bisulfite or some sort of sulfur dioxide or some other chemical to neutralize the chlorine and remove that chlorine residual before you're allowed to discharge. Some plants, I know that Cincinnati, one of their bigger plants, does not have a chlorine residual limit, but I think they're discharging directly to the bottom of the Ohio River, so I assume that that chlorine residual gets used up right away. But anyway, so dosage equals demand plus residual. So uh, let's say that you were feeding 30 milligrams per liter of chlorine and you had a residual of 2 milligrams per liter, then that would tell you that your chlorine demand was 28 milligrams per liter. And the nice thing about chlorine problems, because the dosage is in milligrams per liter, that makes for some pretty simple pounds formula problems. So I would expect to see a fair amount of those on any type of certification exam. As far as available chlorine, that's just basically how much free chlorine is available for disinfection. So gaseous chlorine would have 100% available chlorine. The other popular alternative to gaseous chlorine might be sodium hypochlorite. So much safer to handle than gaseous chlorine, but as you can see by looking at the slide, only 15% of that is available chlorine, so you have to feed quite a bit more. So again, dosage equals demand plus residual. Uh, those are expressed in milligrams per liter, which makes for easy pounds formula problems to be included on exams. Remember your contact time uh, for disinfection, and also chlorine being less effective in colder water temperatures. So finally, we'll wrap up with UV disinfection. So ultraviolet light, uh, again, much safer than chlorine, uh, more expensive to operate. Uh, Ultraviolet radiation is just basically light wavelengths that are shorter than visible light. The theory behind how they work is that these UV light waves alter the cellular genetic material uh, in pathogenic organisms, which makes it impossible for them to replicate or reproduce. Uh, as with chlorine, we're looking at a dosage required to provide adequate disinfection. Uh, with ultraviolet disinfection, the dosage is a function of lamp intensity, or how bright the lamps are burning, times exposure, or how long the contact time is that your effluent is flowing past the UV bulbs. Um, so at least with our system, there's an algorithm that calculates the dosage based on that. There's a sensor that senses lamp intensity, and then, of course, flow, uh, a flow in million gallons per day that it converts to how much detention time that flow has going past the bulbs, and then it will ramp the lights up and down to meet that dosage that the system is set up for to make sure that we get adequate kill. So a few things about UV disinfection. Water that's relatively turbid, so if you have a lot of suspended solids in your final effluent, that can inhibit UV disinfection by scattering the light waves. The light waves have to come in contact with the pathogens. So if you have a lot of suspended solids, those light waves can be bent by the solids passing through, and make it more difficult to get adequate disinfection. Uh, Also, based on the transmittance of the water, so transmittance of your final effluent has to do with how much light can pass through it. So transmittance is not always synonymous with suspended solids. So there are particles in the water that are not going to show up in a suspended solids test that can also absorb some of that light intensity and not allow it to come into contact with pathogens. So we do a test here in our lab called UVT, so ultraviolet transmittance. It calculates the transmittance of the water of our final effluent, and then that is programmed into the control panel that controls our ultraviolet system. And so the lower the transmittance, the more it's going to tell the lights to ramp up to make sure that we have enough of a dose, enough dosage to make sure that we get adequate disinfection. So process control variables for us as operators, again, the UVT of the effluent. Again, we test for that here. If the water has high UVT, then we don't need to burn the lights as brightly. If we have low UVT, then they burn quite a bit brighter. The bulbs, as I mentioned, do get weaker over time until they need to be replaced, so that has to be factored into the calculation. Uh, Quality of the effluent kind of goes hand in hand with the transmittance. High amounts of suspended solids will have an effect, as well as fouling of the bulbs. Now, our bulb, the bulbs are kind of inside quartz sleeves that fit over the top of them, and those sleeves can get fouled with algae. Plants like ours that use ferrous chloride or ferric chloride for phosphorus removal can develop a coating on those quartz sleeves. Anything on those sleeves is, I guess, like having dirty windows. It's going to partially block the light coming through. So our system, and I imagine almost all systems, are designed with a wiping system to wipe those sleeves periodically and try to get them clean to allow more light to pass through. But we do have to periodically pull our light modules and physically hose them down to remove some of that algae that gets stuck around the modules. The wipers do a good job of cleaning the quartz sleeves, but they can't get it all. So that basically sums up UV disinfection. So again, UV and chlorine are the two most common. I wouldn't hopefully expect to see too many questions about ozone because I don't think that's very widely used. But basically, ozone is a gas that's generated at the site if you're using ozone for disinfection, and if you work at a place that uses ozone, I'd love for you to tell me about it so I could understand a little bit more about how it works. But that's disinfection. Next few chapters are on solids handling, aerobic and anaerobic digestion, dewatering, residual solids or disposing of them. A lot of that stuff is no longer covered in the textbook, so I'll probably be doing 3 or 4 different PowerPoints to kind of cover some of that material and try to flush it out for you a little bit. So that's all I've got for today. Disinfection, 22 minutes, so hopefully this helped you out a little bit.